Okay, we're doing part 16 from Prevent and Reverse Hypertension by me, Pete Rogers. We're going to be talking about ion pumps today. By the way, this is the part from the book. If you want a more comprehensive lecture on ion pumps, I made a really good one recently, just called something like Membrane Ion Pumps with an extended metaphor. This is one of these subjects that medical students, biochemistry students often have a lot of difficulty with, and I'm going to tell you the secret right here. I don't have as many pictures as I do in my other lecture, but here's what it comes down to. You have to understand that the extracellular space is like seawater. And being like seawater is salt water. So the extracellular space is high in sodium chloride, but the important thing is it's high in sodium. You have to know that. Everything is based on that. You also need to know that the seawater rinses against the rocks, like the limestone, the calcium carbonate. And when it rinses against the stones, it washes off calcium into the water. So the extracellular space, being like seawater, is very high in calcium. That's like the most important thing to know. And if you remember that, salt water rinses on rocks and puts calcium in the seawater, and that's the same as extracellular space. Everything else that follows is going to make sense. All right, Kate. So then the idea is that God created the first cell with life on Earth. And in order to put new things in there, you have to pump out from the inside of the cell. You have to pump out all the sodium and the calcium. Because you have to have the same osmolality inside the cell as outside the cell. Number of particles and same number of charged particles as you do on the outside overall. But the key point is you have to have the same number of particles inside and outside. Because if you don't, water can pass freely across that membrane and it'll enter the cell and cause it to swell and burst. So the osmotic balance between the number of particles in the cell and in the extracellular space has to be the same. All right, now we can start getting into what happens in the membrane. The sodium-potassium ATP pump runs this thing. And the sodium-potassium ATP pump is going to pump out 3 sodiums and bring in 2 potassiums. And when it does that, you're pumping out more positive charge than you're bringing in. That's going to lead to a slightly net negative charge inside the cell. And that net negative charge inside the cell is called the resting membrane potential. And a neuron is typically about negative 65 millivolts. Okay, the cell devotes a lot of energy to this. It devotes half of its energy, half to 2/3 of its energy. Let's just say 2/3 a neuron to running this pump. So anything that the cell would devote the majority of its energy to has to be super, super, super important. And the reason is it uses this plasma membrane gradient that's produced by this pump as an electrical battery. So the net charge of a battery will have charge, is a sodium net positive charge exiting the cell. This is the barrier, the charge barrier is the plasma membrane. That's the movement of current. It's an electrical gradient, meaning that it's more negatively charged inside the cell than it is outside the cell, negative 65 millivolts. There's a chemical gradient because there's more sodium outside the cell than inside the cell. So sodium wants to come in to equalize its concentration gradient and to approach a negative charge because it's positively charged. And that strong desire of sodium to come into the cell can be coupled to pumping calcium out of the cell. Okay, so this is primary active transport because it uses ATP. This is secondary active transport because it uses the gradient produced by this pump to power this other pump. This is called a NACA exchanger. Na means natrium in Latin for sodium. Ca is calcium. Kalium is K, the symbol for potassium. Okay, so that's why the abbreviation for potassium is K+. It's positively charged, 1+. Sodium's abbreviation is Na+, because it's got a 1+ positive charge, and the Na is for natrium. Okay, and the NACA exchanger is a sodium-calcium exchanger, usually abbreviated NCX. And this little process here of establishing a gradient and then using that gradient coupled to rapidly pumping calcium out. This little pump here can pump out like thousands, let's just say 2,000 to 5,000 calcium ions per second. So it's extraordinarily fast. And it's another reason too, the more you learn about biology and biochemistry, the more you believe in God. Imagine you go up to some biochemist and you say, could you please make for me a nano pump that can pump 2,000, 5,000 calciums out of the cell per second? He'd go, get the heck out of here. Are you insane? God could do it pretty easily. Anyways, that's how a cell manages calcium. And the reason that's going to matter is I'm going to give each of these ions a personality. Potassium is the hard-working, middle-class man, you know, that's daddy, busting his ass, making money for the family while they're all enjoying themselves, okay? Magnesium is like the hero. The friendly neighborhood hero is magnesium. I'll explain why in just a little bit. Sodium is like the angry poor, wants to bust into the house. Calcium is like the aristocrat. You can kind of think of it as a little bit like mama. Big mama is the boss of the family, the matriarch, whatever she says goes. And when mama comes home, it's like flipping on the light switch, stuff has to happen. How come there's dishes on the table? Clean this shit up. You're so lazy. How come there's dog crap on the floor? Clean this shit up. You're so lazy. You know, and so she starts bossing everybody around. She's not reasonable. When calcium comes in, it says what goes, what happens. It's the boss of the cell. That's important to remember. These little things I'm telling you about the personality of ions, it's a very important thing to understand, because this stuff about membrane ion pumps, it's the foundation of all membrane cellular physiology. It's the foundation of neurophysiology. It's the foundation of cardiac physiology. And if you just get these things that I'm saying, these basic introductory metaphors, you'll be able to handle really complex things that other people find difficult, and it'll be easy for you, because I've had multiple medical students come and thank me for this, because they're like, I finally get this stuff. I've been studying this stuff for 2 years, 3 years, you know, from undergrad, and they just don't get it. So you have to know where the ions are, and then everything makes sense. But if you don't have that fixed in your mind, extracellular space is salt water, therefore high in sodium and high in calcium. Once you got that, everything is going to be a lot easier to follow. In my other talk, I have a lot better pictures. I have, you know, like paintings that correspond to the ions. Now, this book was a magnificent book written by Richard Moore, MD, PhD. And before my blood pressure book was written, this was the best blood pressure book on the market. This guy devoted his entire career, like 40, 50 years, studying these membrane ion pumps. He's a brilliant guy, MD, PhD, and he really explained things so well, and how this keys into, you know, hypoxia metabolism, aerobic, which is anaerobic, aerobic metabolism when a cell's in a growth synthesis phase, when it's in a resting maintenance phase. It's a magnificent book. I think all doctors should read it. Chlorophyll is in plants, and magnesium is right in the center of chlorophyll. I can also tell you, I talk to doctors sometimes, like these internal medicine doctors, and they're like, you know, Pete, you're effing right. This is what we should be thinking about, trying to understand these membrane ion pumps, trying to understand the mitochondria, understanding leaky gut and this stuff. They go, you are connecting to all the stuff we really need to know to understand what causes disease and what helps patients. But it's just not in any of our books. And the reason it's not in any of their books is, when you understand the truth about what causes health and what causes disease, then you want to become a low-fat, low-sodium vegan. Okay? Whereas when you don't understand it, then it seems like there's nothing you could do except try these drugs. So the conventional medical textbooks, the allopathic medical textbooks, they perfectly serve their mission to teach people how to deal drugs. Okay, so here's why magnesium is the hero. Because it has a 2+ positive charge, and it holds the negative charges of the phosphates in place. So by holding those negative phosphates in place, it doesn't allow the extra phosphate to be released until the appropriate time in the chemical reaction for running the pump or running some enzyme process. So what I'm trying to say here is, you need magnesium in order to run ATP reactions and to run them correctly. And the vast majority of Americans are deficient in magnesium. Okay? And once you talk about magnesium deficiency, I'll talk about it in some other lecture, but then you start running into the concept of Ames triage theory, and where do you utilize a vitamin or a phytonutrient or a ion. You use it where it's most valuable for the cell, is what his theory is. We'll talk about the Bruce Ames triage theory some other time, but I'm just letting you know this is an important concept. You need magnesium for your ATP reactions, and you get it from plants because it's in the center of chlorophyll normally. Okay, oh, there it is. There's a drawing. There is magnesium located in the center of chlorophyll. Eat your plants, eat your greens, you'll get your magnesium. And you need magnesium for tons of important reactions. Okay? The next thing to talk about is the K factor. K factor is the ratio of potassium to sodium. And Richard Moore believed that you had to keep it at least 5 to avoid hypertension. It's probably best to have it higher, more like around 10. I think our ancestors probably had it around 20. Meat has a K factor of about 4. I think I got pages on it in here, but fruits got K factors, like 100 to 500. All right. Starches are around 20 to 100, and veggies are more like I think 5 to 20, or no, more like around 7 to 20, something like that. So the point is, fruits are super high in potassium, and that's a good thing to prevent hypertension. Oh, and then here was what I was talking about earlier, the amount of osmolality in a cell. It's got to be constant. So the total amount, 98% of the positively charged ions inside a cell are potassium and sodium. Normally there's like 10 times more potassium inside the cell, 10 times more sodium outside the cell. So you can think of potassium as being the key intracellular positively charged ion. That's a cation. Sodium is the key positively charged extracellular ion. But when people eat real high sodium diets that are very low in potassium, they get this sodium drift of more and more sodium getting into that cell, and that will dissipate those gradients, like the concentration gradient between sodium outside and inside the cell, and that'll weaken the plasma membrane electrical battery for doing physical work. You don't want that, okay? And just knowing that it has to stay fixed. There's no way around it. You can't talk your way out of this. You can't take a supplement and get rid of this. It is what it is. This is how the human body runs. This is how all cell physiology is based. And that's why, Dennis Burkett has said, we're the only animal, humans with their modern processed food, that eats more sodium than potassium. Because when you have an intact cell, it's always going to be high in potassium and low in sodium. But processed food, they grind the food, they rinse it with water, they rinse it with solvents, and they rinse away the potassium. And then they add back sodium for taste and as a preservative. So the processed food is going to be high, unnaturally high in sodium and unnaturally low in potassium. And that's going to lead to hypertension, and it's going to lead to poor function in your cells. Also, when a person eats more sodium, they excrete more potassium from their kidneys. And all this leads to a vicious cycle that causes decreased cellular function. Okay? All right, now here is a little bit more advanced detailed diagram of a cell. Intracellular, again, the potassium is about 10 times higher than it is extracellular, and the opposite for sodium, 10 times higher outside the cell than inside the cell. The concentration gradient for calcium is off the charts. It's like 10,000 to 15,000 times higher extracellular than intracellular. And that's why it's such a dramatic big deal when calcium comes into the cell. Whatever that cell does as its main activity, it will be activated when the calcium comes into the cell. And it'll be, for example, if it's a neuron, it'll release its neurotransmitter. If it's a vascular smooth muscle, it'll contract and constrict the vessel. Skeletal muscle, it'll contract. Cardiac muscle, it'll contract. If it's a pancreas beta cell for insulin, it'll release insulin. Okay, and then when you got to get that calcium out of the cell real fast to turn things off, and so you need the knockout exchanger because it's super fast. You've got other pumps to pump calcium. You've got the plasma membrane calcium ATPase pump. You've got the Circa pump, sarcoplasm endoplasmic reticulum calcium ATPase to pump calcium into the endoplasmic reticulum. But the big, really fast one is this knockout exchanger. Okay, so that's the introduction to membrane ion pumps and how they work, the general idea. You might want to hit your print screen button on this one, because trust me, this is the foundation. Neurophysiology, cardiac physiology, muscle physiology, and once you get this, get those little metaphors. Trust me, that can save somebody decades of study to get those metaphors. I mean, I invented those, okay? Then you're going to get this stuff. And once you get this stuff, you'll be able to think at higher and higher levels about cellular physiology, neurophysiology, and much more advanced things. So it's a very useful base of knowledge to have. So hope you found that helpful.